Good morning.
Good morning, sir.
So, welcome back to another week. Uh, in the last week, we discussed about some fundamentals of image segmentation. Last class, particularly, I discussed about how a region R can be split into uh, sub-regions or can be partitioned into sub-regions, and what should be the condition to be satisfied for each region. So we understood that uh, segmentation has to be complete in all respects in terms of the sub-regions. That means if I take the union of the sub-regions, I should get back the complete image that I have partitioned. Um so let us now continue our discussions. Is the screen visible?
Yes, sir.
Okay. So this is what we discussed in the last class. Suppose if you have R as the entire region that I am segmenting, I can partition into sub-regions like R1, R2, Rn, etc. And these sub-regions should satisfy some conditions. The first condition is union of all these sub-regions should get back my image or the region that I have started off, which means segmentation must be complete and each region should be a connected set. Um, Intersection of regions, as long as they are different, should be null. That means they should be disjoint. And the predicate that I am defining, predicate it means it's a condition that I define for any subregion. So for a specific region Ri, this has to be true. That means the condition that you have told. For example, if I am dividing the region based on color, so if I say the values of RGB in that particular region is say some ABC. So for all the pixels in that particular region, it should satisfy. That means the condition has to be true. And if I take the union of regions, that means it should be false because you cannot have the condition to be same for both the regions. So adjacent regions should have different uh, predicate or condition. And I think with a good example of a fruit image which is synthetically generated, in fact I downloaded these images and I have formed into an image. So suppose if I want to classify this image into different fruits, so I define the color range for apple, I define the color range for guava, I define the color range for orange, and similarly for banana, and then put the condition and then verify that condition and segment it. So this is what we discussed in the last class, and we also discussed the difference between edge-based segmentation and region-based segmentation. And two examples, one for edge-based condition, other for region-based condition was discussed. So what you notice here is if the region is smooth here, then edge-based condition will definitely, segmentation will help me to separate them into foreground and background. If there is some noise inside, that means there is some perturbation or some texture that is seen inside the region that you are of interest, then the problem is if I use edge-based segmentation, in fact, every change in the gray level value, it treats as an edge and you will see some noise here. So in such case, it's better you just put a condition that as long as the range of pixels is within some range, you still decide it to be okay one foreground. Then it is easy for us to segment it. So there are two things, and what we understood is a combination of these two would give a better result. So with this, let us continue with the next topic. Um, the next topic is uh, detection of points, line, and edges in an image. Because detecting an isolated point, detecting a line, and detecting an edge is important when you want to segment the objects. So, in fact, if you look at this, what I meant by a point, what I meant by a line, what I meant by an edge. I think with an example I can explain this. So let me go to my OneNote. Okay, so assume that I have an image. This is an image. What is there inside the image is, let us assume that there is a point. So I'll just show this point by using red color. So there is a point here. Okay. Uh, so the meaning of a point is, it would be something like this. Let me just consider an example. 100, 100. This point I show it as white, so I'll make it as 255. So if I have an image something like this, of course these values can be slightly different also. For example, 110, 112, etc. Now this is a point. It is an isolated point because this value or brightness is very high compared to the other values. Okay. So uh, look at this last statement. A line whose length and width are equal to 1 pixel. So I think I should also explain you what is a line. So let me take another example. This is a typical example I am taking just to explain you what we mean by a line. You may not have exactly this type of situation, but anyway. So carefully observe here. What you notice here is, if you observe, there is a pixel variation from 100 to 255. There is a pixel variation from 255 to 100. Okay. So what is happening is, all these are of one color, all these are of other color. Only this particular line that you have, okay, these values, they are of different color. That means it is white. So if you observe this as an image, you would see that you will actually see a white line. So anyway, I'll just show a MATLAB simulation for this. So I'll see a white line at this point, and these values will have different colors. So what you mean by line is, if you just look at the definition, it's actually an edge segment where the intensity of the background on either side of the line is much higher or lower than that of line pixel. Notice here, the intensity of this is much higher as compared to the neighbors. See, this is 255, whereas this is 100, this is also 100. So you see that this intensity is much higher. Of course, it could be the other way also. What I mean by, instead of 255, if all these values were to be 0, then also it is correct. So for example, if I have something like this is 0, again 100, 100, 100, 100, this is 0, 100 or 110. Whatever I am writing, I hope you are able to see it. Are you able to see it?
Yes, sir.
Okay. So what you notice here is, again in this, these values are much lower than the neighbors here. That's the definition. So an edge segment, this is an edge segment because wherever you have sudden changes like this, then definitely there is an edge there. So this speciality of this edge segment is, on either side of this line, you will have much higher or lower values. In this case, you have much lower values. In this case, you have much higher values here. So that is a line. I hope you understood. Now, such a line whose length and width are equal to 1 pixel is a point. For example, in this case, so the length and width of this is only 1 pixel. All other values are different, as you can see. Only this particular pixel has got the highest value and all other pixels are different. Of course, this could be even 0 also. In such case, it will be the lowest value. So a point is, I can call it as a line whose length and width are equal to 1 pixel. And a line is an edge segment where the intensity of the background on either side is much higher or lower. I think I've given specific examples to understand this. Okay. Now, what is an edge? I think you already know an edge. Let me give you an example for it, which I have also given you sometime when we were discussing about low pass filter or effect of low pass filter. Just observe this. So can somebody tell me in what way this is different from a line? Anybody? In what way this is different from a line? This is for these two are for line. This example is for an isolated point, and this is an example for an edge. Anybody? What is the difference between an edge and a line? Okay, at least you can read this and tell me. So edges are set of connected edge pixels where these edge pixels are pixels at which the intensity of image changes abruptly. Just observe here, the intensity has changed abruptly. In a line, what would happen is these values will also be similar to this. That means only this particular line where you have uh, higher values or lower values, whereas the neighbors here will have almost the same values. Whereas in this case, it is something like this. The values are say 100 and at edge it goes to 255 and it almost remains at that. So this is 100 and this is 255. So this is an edge. In a line what happens is, the value will go to 255 but it will come back to 100 again. It will come back to 100 again. As you can see near the line, this value and this value are same. Do you notice the difference between a line and an edge? Any doubt? Can somebody unmute? And okay. So let me just show you a simulation which will probably make it still better. I'll run it for all the values and let us see the images. Okay, so I'll show one by one. Uh, okay, what do you think is this? I think it's clear to you. What is this image?
Line.
It's a line. So you can see I have a white line here. On either side, the pixel values are less. That means dark. So I have a white line here. In fact, intentionally, just to show you the difference, I have taken all these values as I think 50. These values are 50, and this value, all the values on this line, it is 255. That's what I have taken. Just look at the code also. The code is visible here. Uh, look at the code here. So the first one is for the line. What I have taken is I have first generated a matrix which has 50 all the in fact in all the range, and what I have done is In fact, just to make sure that the line is visible to you, instead of taking one one column, I have taken actually three columns: 100, 101, and 102. All these three. So that means it would be something like this. Uh, Let me go to OneNote. It will be something like this. So all these values are 50, 50, 50, 50, etc. All of them. These values are 50. Only the line I have taken three, in fact, columns. I have taken 255, 255, 255. That means just to uh, make it visible, all these are 255. Three columns will have the value 255. So it's a 3 pixel width line, and these values are 50. These values are 50. That's what I have done in this first case. Okay. So these are all 50. These are all 50. On this line, the value is 255. Hope the point is clear. Why intentionally? Actually, I have shown here only one column equal to 255. If I make it one column, no, the width will be very less. Sometimes it may not be visible to you. That's why I have making it as a 3 pixel wide line. Hope it is understood. Okay. Now, what is this? Can you appreciate it? Can you see anything here?
Point.
Yeah, it's a point. Again here, if I had given only one pixel, probably that one pixel in this bigger screen, you would not have noticed it. So that is why what I have done here is, if you look at the code, uh, in fact, around, okay, 254, 55, 56, that means it's a 3 by 3 size point. That means the point is 3 pixel wide. That means it will be a 3 cross 3 point. So it will not be one single point, it would be 3 cross, just to show you. Okay. uh, just to show you, I have just exaggerated it. That means it's just like zooming it so that it is visible. So this is a point, all the values are same, and this value is different. So this could, all of them could be say white, and this value could be black, or all of them could be black and this value could be white. So this is a point. Then the last one is an edge. Okay. Because you can notice here in the last case, all these values are same, all these values are same. So I just see an edge here. That means 50 here and 255 here. So now with this, probably the definition that I have given is clear. So what it says is, okay, I think let me go to the OneNote itself. So what it says is, three types of image features. One is isolated point, second one is a line, third is an edge. So an edge means a set of connected pixels where edge pixels have intensity, abrupt changes in the intensity at near the edge pixels. Now anything that detects this are called edge detectors. Okay, so they are the processing methods that are used. I think we have done it in second chapter. We will be continuing in this chapter also. So edge segments where the intensity background on either side is much higher or lower, it's called a line. I have given an example. And isolate point can be called as a line whose length and width are equal to 1 pixel. Okay, in my simulation I have used it as 3 pixels just to show you. It is an exaggeration, but it should be 1 pixel. So I'll assume that the concept is clear to you now. Now let us continue with our discussions. I think this point is already discussed, so hopefully it should be a revision for you. Now, how do I define these abrupt changes in intensity? All of you know that a first and second order derivative can do it. Let me just demonstrate it with one dimension. Let us assume that I have pixel value something like this, 100, say 200 here, 200 here, 200 here. Now what I will do is, I will use the first order derivative and close approximate to first order derivative in discrete cases. You have to subtract f of x from f of x plus 1. Okay, so if I take this as f of x plus 1 is this, so I have to take a difference. So as you know, 100 minus 100 is 0, again 100 minus 100 is 0, 200 minus 100 is 100, 200 minus 200 is 0, 200 minus 200 is 0. Okay, okay, so this is a first order derivative. Yeah, we also saw in the previous chapter that there you can also go for second order derivative. Look at the formula here. It is f of x plus 1 plus f of x minus 1 minus 2 times of f of x. Okay, so f of x plus 1 minus f of x minus 1 minus 2 times of f of x. So it would be good if you go to this pixel, because you need an f of x minus 1 also. I'll start with this. Let us not let us neglect the border. So what could be the value? Can anybody say what is the value here? Please calculate and tell me what will be the value here. I am doing second order derivative at this value. That means this should be taken as f of x. This will be your f of x plus 1. This will be your f of x minus 1. What is the value? What is the value here? It's a simple formula and you know the values. Can somebody unmute and tell me?
0, sir.
0, because 100 plus 100 minus 200. So this is 0, correct? What is the value here?
100.
200 plus 100, 300 minus 200. This will be 100. The value here?
100.
200 plus 100, 300 minus at this point I'm telling 200 plus 100, 300 minus
100.
100. Here
0.
correct. 200 plus 200 is 400 minus 400, it is 0. So let us not worry about this border pixel. Even here also let us not worry. These are all the border pixels. There is a different way to tackle it. I can even tell you now only. What they will do is, whatever value they have in the border here, they will assume that the next pixel is also 200. Whatever is the value here, they'll assume that the previous pixel is also 100 and do the calculation. But anyway, let us not worry about the border. We will only consider this portion. Now carefully observe what is that I have taken as an example. These values are 100 and these values are 200. So if you look at it as a 1D plot, it is something like this. So this is 100 and these values are 200. Okay, and I have just passed through a simple derivative operator or difference operation. This is what I have used. This is the first order derivative and this is the second order derivative. Anyway, we'll see the difference again. We have seen it in the previous chapter also. Sorry, in the second unit, we will see it again. But what you should notice is, this is where you have an edge. The pixel is changing from 100 to 200. So there is an abrupt change here. Now, if you observe first order derivative, at the onset of the abrupt change, you are seeing a non-zero value. Wherever the pixel values are same, you are seeing 0. Wherever the pixel values are same, you are seeing 0. Only at the point where you have an edge, it is giving me a non-zero. So this means that I have detected that there is an edge at this position. Now if you compare this with the second order, here also wherever it is same, it is giving you 0, and wherever there is an edge here, it is actually giving you non-zero. But the only difference is you see an effect called double edge effect. This effect is called double edge. We have discussed this in second unit also, wherein you see a positive value, you see a negative value also. That means it goes positive and comes to negative, and so this type of observation is seen. This is called double edge effect. Okay, so what this tells me is, by using first and second order derivatives, I can identify abrupt changes in the image. That's what is important, and that's what you have done in unit 2 also. To detect edges in an image, we have used this. So this is the first order derivative, this is the second order derivative. The only difference is, since the image is not a continuous image, it's a discrete image, the derivative operator is replaced by difference operation. Difference is equivalent to difference derivative. Okay, but there is a problem with this difference operation, which we will discuss now. I hope you remember this example, which we had discussed even in the unit 2 also. Okay. If any of you remember it, can you just tell me what is that we learned here? Can you explain this? I'll be happy if one of you explain it. What is it we learned in this particular picture? Anybody? This was a repetition. We have done this. Nobody remembers it or don't want to try. Okay, so let me explain. What is done is, this is an image. Okay, okay, scan line is taken here, and the scan line where it is taken is at this point. This point the scan line is taken. This point the scan line is taken. I'll remove it because you need to see the changes there. So notice here that the brightness is gradually decreasing, then it is constant here, and I hope you can also see that. Let me just slightly zoom it. Hopefully you can see. Do you see a white dot here at this point?
Yes, sir.
Yeah. So at this point there is a white dot. So hopefully it is visible to you. So suddenly at this point the value suddenly increases and comes back. So this is actually a point that I discussed, an isolated point that I discussed just now. Then you have the constant value. Then you could see that there is an edge here, and this type of edge they actually call it as rooftop edges or triangular edges, because intensity gradually increases and comes back. Okay, something which we notice. Then again it is constant, and suddenly at this point the brightness is increasing. So carefully observe this right side point. Initially it is constant, and then it is gradually decreasing. So you are seeing a gradual decrease here. Then it is constant at almost 0. Then suddenly there is an isolated point where the pixel increases and comes back. Normally in an image like this, if you see an isolated point like this, it would be a noise pixel which has to be taken care. Then again it is constant. Then, as I said, there is a a rooftop type of edge, then it is constant, and then suddenly the gray level value is increasing to maximum. So this is a 1D plot of this particular scan line. So now let us understand the difference. So instead of a continuous image like this, what you see is a sampled version of this. So an example is taken here. These values are examples. So let us assume that this value, okay, is 5. So that's what you see, it is 5, and it is gradually decreasing. So it is decreasing to 4, coming to 3, 2, 1 and 0. Then it is constant at 0. Then it increases suddenly to 5 back. So this is that isolated point. Again come back to 0. Then it is constant. Then you have okay, rooftop type of it. That means it first increases to 1 and then it increases to 3. Again it comes back to 3. Then it comes back to 1. Okay. The difference between this and this is this. Suddenly it goes to 5 and comes back. Whereas here it is gradually going to 3 and coming back. Okay. So that's why it's called rooftop edge because it looks like the top of a roof. Not a flat roof, tiled roof. Uh, Again it is constant and there is a sudden edge. From 0 it goes to 5 and remains at 5. Okay. So the values are shown here. 5, 5, 4, 3, 2, 1, 0, 0, 0. This is 6, then 0, 0, 0, then 1, 3, 1, then 0, 0, 0. The others are 7. Now let us take the first order derivative. So it is f of x plus 1 minus f of x. So you are starting from this point, because if you start from this point, it is difficult to find the second order derivative. You saw the example that I explained. So that is why you are starting from this point. That's okay. The edge pixel can be in fact neglected. So 4 minus 5 is minus 1. 3 minus 4 is minus 1. 2 minus 3 is minus 1. 1 minus 2 minus 1. 0 minus 1 minus 1. 0 minus 0, etc., etc. I think it's not difficult for you to understand this. Now this is the first order derivative. Second order derivative, all of you know that you have to add these two. 5 plus 4 is 9. Okay, 9 minus of 2 times of this. So 5 plus 4 is 9. 9 minus of 10 is minus 1. If you go to this point, 5 plus 3 is 8. 8 minus of 8 is 0. Okay. Again, if you go to this point, 4 plus 2 is 6. 6 minus of 6 is 0. So I think you know how to write this. For example, if you go here, 0 plus 0 is 0. Minus of 2 times of this is minus 12. Okay. Not a difficult thing. So please observe what is the example image that is taken here. You have taken a ramp type of edge. So this we call it as a ramp edge. That means it is gradually decreasing as a slope. This is called an isolated point. So, that means only this pixel value has got highest gray level as compared to the neighbors. So it's an isolated point. And this is a thin line segment. It's not an isolated point, it's a line segment where the pixel value is increasing and coming back. And this is a step edge. So you have a ramp edge, you have an isolated point, you have a step edge, and you have thin line flat segment. Now just observe what happens near the ramp, what happens near the isolated point, and similarly what happens near the step and also the fine line segment in first order derivative and second order derivative. Now what do you notice here? When the ramp starts, okay, the first order derivative has become non-zero, and as long as the ramp is there, the first order derivative continues to be there as the same value. Observe, from here to here all the values are same. Wherever the input is constant, then the corresponding first order derivative is 0. Near the isolated point, what you see is there is an edge, as you can see. When it is 0, it is 0. When it is constant, it is 0. Only when there is a step edge, you could see a non-zero value here. This is first order derivative. Now coming to second order derivative, this is where the ramp is starting. So the point at which the ramp is starting, it is non-zero. This is where the ramp is ending. The point at which the ramp is ending, it is non-zero. Whereas during the ramp region, the second order derivative is 0. Because all of you know, this is not a difficult thing to understand. Suppose if I have an equation like x is equal to at. What is this equation? Can somebody tell me? Equation of what? It looks like y is equal to mx plus c. So what is this equation? Y is equal to mx plus c. Anybody?
Equation of a line, sir.
Straight line, sir.
It is a straight line. So this is also a straight line, except that the constant is 0. That means the straight line is passing through the origin. That's all the difference. So this is a line, straight line. Or you can say it's a ramp. X is equal to at means it looks something like this. Okay, this is x is equal to at, where a is the slope. Now if I differentiate this with respect to t, okay, so what is dx by dt? A, correct? Now a means it is constant. That is exactly what you see here. It is constant. Second derivative means I should differentiate it again. So I should find d square x of dt square. So what is d square x of dt square? It is 0, because differential of a constant will be 0. So that is why you see in the second order derivative, near the ramp region, it is 0. So the observation is, okay, I think we will just complete this observation and stop for today. So these are the observations. Please understand, first order derivative is non-zero at the onset and along the intensity ramp. This is what you have seen. Not only the near the ramp, entire along the region of the ramp, it is non-zero, all the values. Whereas second order derivative is non-zero only at onset and end of the ramp. That's also you have seen. This we have already discussed in the previous unit, that is second unit. So only in the onset and where it is ending, it is non-zero, but along the ramp it is 0. First order derivative produces thick edges, whereas second order fine edges. So now you can observe that this is a ramp. So when you just show this first order derivative, it looks like this. It has become -1 and then it has become 0 like this. So this is an edge which is thicker. Okay. So first order derivative produces thick edges compared to second order. It produces fine edges. This is an advantage of second order derivative. Magnitude of the response for isolated noise point is much stronger. Now observe the isolated point. This is the isolated point. What do you notice here? It is changing from 6 to -6. So what is the delta change? The delta change is 6 minus of -6 is 12. This is the change that happens in an isolated point in first order. What about second order? The delta change that you have is 6 plus 6, 12, minus of -12 is 24. The change is so much. The change is so much. It's going from 6 to -12 and coming back to 6. So, no, sorry, it is not 24, it is 18. I'm sorry. Because it's coming back to 6. Okay. So the change is, it is changing from 6 to -12. So the change is 18. So you can see it is much stronger as compared to this. That means the effect of second order derivative on noise point is very high, which is a disadvantage. This is an advantage, produces thin edges, sorry, this one, but this is a disadvantage because it is very sensitive to noise points, which is a disadvantage. Now second order enhances finer details. much more than first order. Of course, the disadvantage is including noise. So this is a disadvantage. Second order has a larger magnitude for line. That's what we have seen. It introduces double edge effect. So you could see the double edge effect here. It goes to minus, comes back to positive. It goes to minus, comes back to positive. So this is a double edge effect. Light to dark transition yields negative second order derivative, and dark to light yields positive second order derivative. Okay, just observe here. This is from dark to light. Okay, so dark to light, you can see what is happening in second order derivative. Dark to light, you have positive change. Dark to light, 0 to 7. So I hope the observations are clear, which are very clearly explained in this. So even though there is a disadvantage that you have the sensitivity to noise, normally what they do is they will first pre-filter the image. That means they'll first remove the noise and then they will apply a second order derivative because of this advantage. Because it produces finer edges, which is very important whenever you are detecting objects, particularly when you are using this segmentation for medical imaging. You have to very clearly identify the border and make sure that your accuracy, the segmentation accuracy is good. So finer edges are expected there. Therefore, second order derivative is usually used as compared to first order derivative. So with this, let us stop at this stage.